Thank you very much, Lorenzo, for the introduction. Thank you for the three of you, Lorenzo, Annette, and Martin, for the invitation. Hopefully, we can do this again in person one day. But okay, yeah, this is already quite nice, and yeah, series of seminars, plenty of very nice talks. So I am going to present joint work with Jérôme Poineau, and I have given this talk at least another occasion. So for people that already were there, I apologize for the overlapping. There will be quite a bit of overlapping with that, but yeah, I changed my Beamer style for that. I have used the Frankfurt theme for this one, so just to feel a little bit more closer to the original format of the conference. So yeah, so what is the talk being about? Well, it's about a description of Schottky uniformization of curves and the similarities that appear between the Archimedean and non-Archimedean words in a more precise context than just looking at the similarities, which is the context of Berkovich spaces over Z. So I won't assume any previous knowledge of this. I will introduce what a Schottky uniformization is, how it works in the Archimedean and non-Archimedean words, and then I can tell how we frame this in the context of Berkovich spaces over Z, which is a theory that was introduced by Berkovich and studied first in a programmatic way by Jérôme Poineau. And I will talk about our construction of this object, this universal Mumford curve over Z. So this is plural just because there's one for every genus, but for a given genus, there's only one. So I think that's universal enough. And I will talk about the relationship with the more tropical aspects of the theory, and in particular with the so-called outer space. I will tell what it is when we get there. So first of all, Schottky uniformization. What is that? The starting point is the uniformization of curves in the complex setting. This can be described in many ways, but a classical example is what happens with an elliptic curves, right? So we can start from an elliptic curve over the complex numbers, given, for instance, by this cubic equation. We want that this cubic is non-singular. So we ask that the discriminant is different from 0. And then we have this very nice classical result that says that the complex point of this elliptic curve form a group. And the group can be described in very explicit terms. It is isomorphic to the quotient of the complex plane by a lattice. So you can just picture a fraction of the complex plane that is bounded by the lines joining the points of this lattice, and then you do you just identify the ends and you pairwise identify them, and so you get a torus. So this is what classically happens in the case of elliptic curves. And one can should remark two things at this point. The first thing is that the elliptic curve has been defined as an algebraic object, but this isomorphism is actually of an analytic nature. So we are bringing analytic objects into play. In particular, in this case, we have the Weierstrass P function, which is not a polynomial, it's a meromorphic function. And it satisfies a certain differential equation, which is algebraic, so gives us back the equation of our elliptic curve. And the second thing is that if we look at this uniformization and we apply the transformation exponential to the 2 pi I dot, so z goes to e to the 2 pi I z, then we can write this in multiplicative form. So our group of complex points of the elliptic curve can be described as the quotient of C star by multiplication by an element Q. And the relationship between Q and tau is explicit. Q is e to the 2 pi r tau. But this works in the case of engines. So if we have a compact Riemann surface of genus G, we have the so-called Rückerschnitt theorem of Koebe that says that we can describe this curve as a quotient of an open dense subset of the complex plane by the action of a free group of rank G. And so this free group of rank G cannot be like any group. There are some special subgroups of PGL2C that realize this uniformization, and these are what are called Schottky groups. So this is also known as Schottky uniformization, and we'll get back to this later. So this is the very, very classical setting. Koebe-Rücknerschnitt theorem is of the first decade of the 20th century. So the question now is, what happens if we replace the complex number with a different field, or if we dare even a different ring? Then the first big problem that we have is that all this complex analytic structure seems to not be available anymore, right? So that's where things start to become more complex. And the first thing we need is a nice notion of analytic geometry over say, maybe a non-Archimedean field or even a ring. So maybe we can ask what kind of ring can we take. And so there has been a lot of attempts historically to tackle this problem. Yeah, as far as I know, the first theory of analytic geometry over non-Archimedean fields was introduced by John Tate in the 60s, and his motivation was precisely uniformization of elliptic curves. So he was motivated by this question, and just in the case of elliptic curves, he did some computations, and there were some very nice analogies between non-Archimedean and Archimedean uniformization of elliptic curves, and so he decided to go deeper into this and came up with a very, very nice theory of analytic geometry that is referred to as original analytic geometry, which has been linked to formal algebraic geometry by Michel Renaud in the 70s, and a lot of applications issued from these. The main issue with Tate's theory is that he had to introduce a Grothendieck topology. So these analytic, rigid analytic spaces, they are not topological spaces, but they have something called a Grothendieck topology on them. So yeah, so I mean, you can do a lot of things, but when you start thinking about, for instance, group acting on, say, the projective line or a fine line, then it's nice to have a theory that also has some nice topological properties. And this is what Berkovich theory does. So this is a theory that is much more recent, uses spaces of evaluations, and it's very nicely related to rigid analytic geometry in a very precise way, and has the advantage that Berkovich spaces have a topology. It makes them particularly nice in most cases, and we're going to see this. Just to finish the history, there's also a theory of Roland Huber's adic spaces, and then there is the generalization over Banach rings that has been studied by Jérôme Poineau, and in other cases for other Banach rings, there are other authors that did this. I should probably mention also the work, very recent work of Clausen and Scholze about analytic geometry. In the case of, they are building up a very nice commutative algebraic machinery to tackle a lot of problems in this setting. But yeah, I'm guilty of not having started trying to learn that. So I didn't include that in the slides, and I don't think I will be able to answer any questions of relation to that theory. But certainly, it seems to have more than a relation with the theory of Berkovich spaces over Z and similar theories. So I suspect is quite connected with the things that one can do with the Berkovich spaces over Z. Well, this is the story of the theories, but there are actually a lot of applications that could be a lot of things that could be solved with this analytic approach to arithmetic geometry. So, in the form of perfect spaces or Berkovich spaces, there has been a lot of application to arithmetic geometry. There are certainly applications to algebraic geometry. There are a lot of connections with toric and tropical geometries. I don't think I have to convince any of you about this. So there are a lot of directions, and so these theories have been proven really fruitful. And the reason, I think, is that analytic methods are really everywhere in a lot of places in algebraic geometry, but also hyperbolic geometry or differential geometry. So this is really, by establishing something that is related to analytic geometry, one can go in a lot of different places. All right, so before I start talking and defining properly what is a Berkovich spaces over a Banach ring, then maybe this is a good time to stop and see if there are any questions. Okay, so let me recall what our aim is. Our aim is to find a common framework for Schottky uniformization. And to do this, we have to introduce analytic spaces. And if we want to do something that is Archimedean and non-Archimedean at once, maybe we want to study analytic spaces over a ring of integers of number fields, for instance, over Z. So we have to define what is an analytic space over a commutative Banach ring, say with unit. And for the purpose of this talk, I don't need to talk about the category of Berkovich spaces over Z. I will do something more concrete, and I will talk about what is the analytic space AN analytified over A, and maybe describe some of subsets that we can find inside this space. So as a set, this is quite easy to describe. AN analytic over A is the set of multiplicative semi-norms from the polynomial rings with coefficients in A to the positive reals that are bounded on A. So if I take the restriction of this semi-norm on A, this is bounded by this norm with the double signs. Yeah. Then it's also a topological space, of course, and the topology on it, probably the shortest way to describe this is that it's the weakest or coarsest topology, such that our evaluation map from our affine space to R plus given by every F as evaluating our norm in F, they are continuous. And then, of course, we also want a structure sheaf of rings, and this, as in the classical case of analytic geometry, say complex analytic geometry, is described as the sheaf of functions that are locally limits of rational functions without poles on U. So if we do this, we find that with this topology, the space, the affine space in n dimensions over A is a Hausdorff space, locally compact and locally path connected. So this is quite nice, especially if you think that A can be any boundary, right? So, for instance, it's quite remarkable that if one starts from a non-Archimedean field, even which is with the non-Archimedean topology is something that is totally disconnected, one can still end up with a space that is, for instance, locally path connected. And the reason basically is that we are adding a lot of valuations to the the kind of scheme theoretic affine space to it that makes this kind of space connected. Then another object that... I
think there's a question in the chat.
Oh, yes. What is that?
It was on the previous slide. It was the evaluation of F.
Oh, no. This is, so this is, the norm is not fixed. So the evaluation is a map that takes a norm and gives back the norm of F. So F is...
Oh, I see. Okay.
Mm-hmm.
Yeah.
So I'm not fixing anything. All right, so another object that is of interest to us is the so-called complete residue field that will give us some algebraic information about points in our space. So to each point, we can associate such a field that is defined as the completion of the fraction field of the polynomial ring divided by the kernel of the corresponding norm. So here I'm just, abusing notation and calling X a point, but the corresponding semi-norm is absolute value sub X. So yeah, so I just said that we are not assuming that these are norms. So there might be a kernel to it. And so to find the fraction, the complete residue field, we have to quotient by this kernel. All right, and this comes naturally with an evaluation map, right? That's just obtained by composing all these processes that we get from going from the polynomial ring to the HX. So some examples of this. So if we take the 0th dimensional affine space over the ring of integers of Q, then what we obtain is something that looks like this. because now we're not looking at any polynomial ring. We're just looking at norms, at multiplicative semi-norms on just A, okay? So 0th dimensional means that there are no variables involved in this. So, and I am considering Z with the usual Euclidean norm. So I am looking at all the norms on Z that are bounded by the Euclidean norm. So what can I take? I can take a Euclidean norm raised to the power epsilon for some epsilon between 0 and 1. And then this will give me something that is homeomorphic to a real interval that connects the Euclidean norm with this norm 0, which is... And then we know by Ostrowski's theorem that we don't have, well, we have infinitely many other norms, but modulo equivalence, they are just the p-adic norms. So where do this p-adic norm sit? They are basically between the trivial norm and those semi-norms that have kernels prime numbers. Right, so we can consider for a prime p the p-adic norm, and then we can raise it to the power epsilon. And then if we move epsilon from 0 to infinity, then we are just moving along this edge, which is actually also something that in the Berkovich topology is homeomorphic to a real interval. So basically for points that are inside a given segment here, a basis of neighborhood is just given by the same thing that it will be by looking basis of neighborhoods over real intervals. However, basis of neighborhoods of this central point, if you think about the definition of the topology, then they must include infinitely many branches, completely infinitely many branches, and then they might cut a finite number of other branches. So at most finite numbers. And what the other thing that is interesting about this is that we can have a look at the complete residue fields. And for points with Archimedean norms, in the case of Z, we have R. For the central point, we'll find Q, trivially valued. And for the p-adic point, we have p-adic numbers, and the extremal points here associated to semi-norms that are not norms are finite fields. So this is kind of an object that is relatively simple, but already encodes, yeah, I find it quite fascinating because it encodes the Archimedean and non-Archimedean words at once. So it looks like a good object to, try to describe phenomena that have very close analogs and between the Archimedean and the non-Archimedean words. And so if you now you try to raise the dimension here, and you go up and you try to think at what is the affine line over Z, say, then, well, this will be your base space. So any space over Z will be fibered over this kind of a star or broom or whatever you see it in it. So for each point in the base, you have a fiber that will be, for instance, in the case of A1, will be isomorphic to the analytic A1 over R, or A1 over Q trivially valued, A1 over QP, or A1 over FP trivially valued. And of course, in the non-Archimedean setting, these fibers are Berkovich spaces. And in the Archimedean setting, then they are complex analytic spaces, quotiented by, possibly quotiented by the involution I goes to minus I. Okay, so what are, for instance, fibers over p-adic points here? Well, to find them, we have to consider our Banach ring to be QP, say, so to be a non-Archimedean field, and look at what is, for instance, the affine line or the projective line over QP. So it's something that looks like this. It's a picture that is familiar to people that have seen Berkovich curves, but maybe not all of you have done this. So I included this. And yeah, here I just say that this P is different from 2, because if you can see here, there are some 2s, and it won't be true that they are as, oh, and maybe P is also different from 3 because I have a P minus 1 here. So if a P is equal to 3, then it's equal to 2. So they should be in the same place, but okay. The idea is that there are different points, and they're, if they are close for the p-adic topology on QP, then the shortest path from those two will be, in a certain sense, shorter. So they will meet earlier. So yeah, so you find this kind of infinite tree. So there is this celebrated theorem of Sam Payne that says that analytifications, Berkovich analytifications are limits of tropicalization. So this is really, if you're more familiar with tropical geometry, you can think about this as a limit of tropical objects that naturally live inside the Berkovich space. What happens for other kind of curves? Here I've written something that is an elliptic curve, and is an elliptic curve uniformized as in the case of complex elliptic curves, right? So this is like QP star quotiented by the multiplication of a certain element of QP. So yeah, I will try to explain in a minute why this curve has these shapes here. But you can see that there is a loop, and then from this loop you have things that look locally like pieces of this projective line that stem from the loop. And more in general, since you can think about this as limits of tropicalization, you have some finite graph inside your Berkovich curve. If you want to start thinking about Berkovich curves, that's the way I do. So which is called the minimal skeleton, and then from it you have some sort of infinite trees that stem from that. So the topological picture is more or less like this. And well, if you want to have an explicit equation, then you have something of this form. And yeah, so you might remark that this is a special equation because it is the equation of an elliptic curve with multiplicative reduction here. So the reduction is not an elliptic curve here, but it's a node. So this is certainly not a coincidence. Okay, so I will start talking about how to patch together the different Schottky uniformization in the Archimedean and non-Archimedean words. But first, I should pause to see if you have any questions.
Maybe just an informative question. Is there like an intrinsic theory of non-Archimedean spaces over Z at this point? Or is it just analytifications of algebraic things?
There is an intrinsic theory being developed, you know, like a category of Berkovich spaces over Z. Yes, there is work of Thibault and Manissier, and there should be, so there is probably, I don't know if it's an upcoming asterisk or it will be, but by Jérôme Poineau and Thibault and Manissier about precisely about this. There is a paper on Archit by them that try precisely to do this.
Okay,
yes.
Thanks.
Right, so and let's start to see what is this Schottky uniformization in the non-Archimedean setting. So there is this theorem of Tate, which is one of his main motivation to invent rigid analytic geometry, that says that basically what we've seen in the complex picture is true also for non-Archimedean fields. So let's start by taking a complete non-Archimedean field. You can think about it as QP, or if you prefer equicharacteristic, maybe Lorentz series or Puiseux series, whatever you want. It doesn't have to be algebraically closed. Then, if you have an elliptic curve with split multiplicative reduction, sorry, then this theorem Tate says that it can be uniformized in this multiplicative fashion for a certain element of K with absolute value between 0 and 1. So I think it might be instructive to see. Let me see, I should have done new share, but this should work too. Okay, so if this works, I'll show you what is why do we get the picture that we had before. So if you think about the multiplicative form of the complex uniformization, you start with the multiplicative group over C, which is the Riemann sphere without 0 and infinity. And then maybe you have an element Q here. You can consider the annulus here. I don't know, maybe one is here. So just look at this analytic subset of GM. The annulus given by, well, basically all the complex point, such that the absolute value is between the absolute value of Q and the absolute value of 1, which is 1. Then, well, okay, by considering also the, by taking this, the closed annulus, and identifying these two circles, you get precisely this thing here, and probably the image of the circle is something like that. Look like this. All right, so we just sliced our sphere, and then we identified these two circles, and this is what we get. So in a certain sense, is a partial uniformization with respect to what we had with the torus. Well, with the with C quotiented by the lattice. All right. So in this case, we have the analytic curve given by GM. So if you want C star quotiented by Q to the. Okay, so let's do the same in the non-Archimedean setting. Then you have a subset of our P1 or A1 over QP that we saw before. And Q is at a certain distance from between 0 and 1. And so our annulus looks something like this. It is kind of this slice of our curve. So when we quotient by multiplication, so now our elliptic curve is, QP star divided by, well, if you want the Berkovich, we want a little bit more, but okay, by Q to the Z. Then what we're doing, we are identifying the boundary points of this annulus. But due to the non-Archimedean property, basically the boundary, I mean, we are, okay, we identify, so we have some sort of space that retracts over a single point here, and here we have everything that retracts here, and we are saying that this point above is equal to the point below. So basically, this, maybe I should find another color. So this yellow segment becomes our skeleton, and everything else are, the thing that already stem from this segment, they are mapped there. Okay, so this is very briefly why the picture of a curve with Tate uniformization looks like this. Okay, so any question about this? Okay, if not, let's mention that there is an analog of Tate's theorem for higher genus curves. It's this beautiful theorem by Mumford that is actually in more generality than just over a non-Archimedean field, that says that if you have a smooth projective curve of genus G, whose Jacobian has totally degenerate reduction, then you have an open dense subset of P1 analytic over K. So I'm stating it in the language of Berkovich geometry actually, but the original theorem was due to Mumford. So this open dense subset can be, there's a subgroup of PGL2K free of rank G that acts on it with some extra properties that make it a Schottky group, and such that the analytification of our curve is isomorphic to omega quotiented by gamma. Okay, if you want to state this in the original setting, you need some formal geometry. But in the case of Berkovich geometry, you have an actual action of the group over P1 analytic, and it acts in a good way, and so you can talk about this very freely. So our aim is to build a universal theory of this kind of uniformization, Schottky uniformization, that works for every valued field, both Archimedean and non-Archimedean at once. Okay, let's go. So the first thing that we need to do is to explain what are these kind of groups that that occur in Schottky uniformization. So these are the so-called Schottky groups. So if we start with a complete value field, and we are looking at the action of PGL2K over the analytification of the projective line over K. So a Schottky group is a subgroup of PGL2K that satisfies the following properties. So it is a finitely generated free subgroup. You want all non-trivial elements to be loxodromic. It means that if you look at the quotient of the two eigenvalues, which is well defined even for elements of PGL2, sorry, the absolute value of two eigenvalues are different. So of course the eigenvalues are not uniquely defined, but the fact that their absolute value is different works well. And we want that it acts on P1. Yeah, so that the locus where gamma acts on P1 in properly and discontinuously is non-empty. So this actually implies that is a dense subset of P1, and that the complement, so the points where the action of gamma is not properly discontinuous, which we call also the limit set, is a compact subset of P1 and contains only k rational points. So you can think of L as a subset of points that lie at the end of this kind of infinite tree, which is P1 analytic over K. Okay, so what does it mean to be loxodromic? I said that the eigenvalues have different absolute values. So if I take the quotient of two eigenvalues, it doesn't have absolute value 1. It can be higher or by choosing the right quotient, we can take the one that has absolute value strictly smaller than 1. And then
Daniele, there is a question or remark in chat.
Yes. Yes, that's right. Yeah, so when I say totally degenerated, in the case of this was in the case of a Mumford theorem, right? So the curve needs to be has a split totally degenerate reduction. So we can think maybe of the case of a residue field of our complete value field to be algebraically closed, for instance. Yeah, sorry. So where yes. So if we have one element of BGL2K that is loxodromic, then it acts also has two fixed points, and one of these points is attracting. So all the points of P1 move toward alpha, and another one of these fixed point is repelling. So all the other points move from alpha prime, and basically the datum of this alpha, alpha prime, and beta gives us all we want to know about our loxodromic element. So it allows us to determine explicitly our matrix. So there are some formulas that are known as Schottky coordinates that allow us. So there are, alpha, alpha prime, and beta are what are known Schottky coordinates, and from the Schottky coordinates we can describe a matrix M alpha, alpha prime, beta. And explicitly, this is what the formula gives. So it's just you can just check that this is the matrix that is conjugated to the matrix multiplication by beta, basically in P1. And this is useful for us because we want to start our define our to describe uniformly this Schottky uniformization by finding a moduli spaces for these Schottky groups. And these moduli spaces already exist in the Archimedean and non-Archimedean case, and we define them over Z as follows. The Schottky space will be the subset of the analytic affine space over Z of dimension 3G minus 3. So here I am taking G greater or equal than 2 to make sense of this dimension here. And so this subset consists of the points, right? So these are all the coordinates. So if you think about this, are 3G minus 3 coordinates. Is a kind of strange way of writing 3G minus 3 coordinates, but it makes sense because we want these points with this coordinate to be inside the Schottky space if the subgroup defined by matrices in terms of these Schottky coordinates is a Schottky group. So we are just fixing 0, 1, and infinity. 0 and infinity as attracting point, attracting a repelling point of the first matrix, and 1 as the attracting point of the second matrix. And yeah, we just choose those points such that this makes a Schottky group. And then the first thing that we can remark is that if we fix any valued field and any Schottky group inside PGL2K of rank G, then we can find a corresponding point in the Schottky space, possibly base changed with K, such that you know, the corresponding such that up to a reparametrization, the Schottky group corresponding to gamma Z, so this Schottky group here is our Schottky group. Okay. So yeah, this is not too hard to see, but it's something that we had to check to say that this is a space of Schottky groups. And then we proved that the Schottky space is a connected open subset of 3G minus 3 dimensional affine space over Z. So it is not such a bad subset. There are some kind of inequalities with cross ratios involved inside. There are some extra properties like stratifications that one can have a look to understand better this space. But the first thing we wanted to use it for is to describe the uniformization, right? So we have the space of Schottky groups. And so what happens in the case G equal 1? In the case G equal 1, we just have one parameter, right? Because we can fix 0 and infinity as attracting and repelling points. So we just have our parameter beta. So basically S1 is the pointed unit disk. And right, and then we can consider the relative projective line over S1. So the relative projective line over S1 allows us to describe the uniformization, the Tate uniformization in a sort of a universal way. So we can consider this relative P1 minus the 0 and infinity section. And then there will be a natural action by the multiplication by T1 over Z. So Z in this case is the parameter of P1, and T1 is the parameter associated to S1. If we quotient it by this multiplication, then we get a very interesting space, which is some sort of a universal Tate curve. And we can do this in more generality in the case of G greater or equal than 2. So just the notation is more burdensome. We can describe a universal Schottky group, which will be a subgroup of PGL2 O of SG, and then it's generated by, abstractly by a certain number of variables. And then we can establish this universal uniformization as follows. So we basically want to show that the limit subset for this uniformization varies in a continuous way. So we established the existence of a universal limit subset, universal limit subset, limit set for the action of this gamma, which is a closed subset of P1 over SG obtained by base change of P1 to SG, such that, well, we retrieve the limit set of gamma Z for each fiber over Z. And when we take that out of P1 analytic over SG, so you see here, it was just a constant section 0 infinity, but we have to generalize this in some way. So this L, when we take out of P1 analytic, we have an action of big gamma, which is still totally discontinuous. And when we quotient by this action, we find a curve that is over SG and has the property that for each point of SG, the pre-image here is precisely the curve uniformized by the Schottky group corresponding to this. So we basically have a space of Schottky groups, and then we have a universal curve over it that that describes the uniformization, the uniformized curve in in a continuous way. Sorry. Okay, so yeah, the last part is basically I intend to describe more tropical aspects of this theory, and the story starts with the fact that the group of outer automorphism of the free group with G generators acts analytically and properly discontinuously on the Schottky space, right? Because a point in the Schottky space represents a Schottky group which is marked with a set of generators. So out of G can swap the generators or can just combine them to find another presentation for our Schottky group. So there is an action of out of G, and one can show that this action is actually respects the analytic structure of SG, and that there are stabilizers. So the action is not free, but the stabilizers are finite, and basically they are related to the automorphism groups of the corresponding Mumford curves. So we can take the quotient of SG by that. We start by looking at this as a topological space for the purpose of this section. But it's still a space that parametrizes Mumford curves on the non-Archimedean part. So basically here we are, the action of out FG takes out every ambiguity of that there might be in the space of Schottky groups. And in the Archimedean place has a little bit more of information, which is kind of reminiscent to putting a level structure on an elliptic curve in a certain sense. So MUMF-G is not the moduli space of curves MG, but it covers the moduli space of complex curve in the Archimedean part. So yeah, so there is this action of the outer automorphist group of FG, which is a group that has been studied also in the context of geometric group theory. And in geometric group theory, it appears as when studying the outer space, which is something that Kuller and Voskman started to do in the 80s, and they have a lot of very nice applications to this object that they construct, which is the outer space. And they construct it as to have some sort of combinatorial object where the group out of G acts. So this is a space of metric graph of genus G that are also endowed with a marking. So basically, a marking is an isomorphism between the free group and the fundamental group of this metric graph of genus G. So we can relate these two objects by saying that if we have our complete non-Archimedean valued field, then each Mumford curve of genus G retracts onto this canonical skeleton, the minimal skeleton I was talking about earlier. And so we get naturally a morphism between SGK and CVG. So this is the SGK is the base change of SG with our non-Archimedean valued field. So here we're just working over a fixed non-Archimedean valued field. So by looking,
there is another question in chat.
Okay, that's a very good question. Maybe I should try to answer that later because this is the last slide. So, but yeah, I'll keep that question. Thank you, Antoine. So yeah, so we have a surjective continuous map that is given by over this this fiber product, where the arrow over CVG is this one, and the arrow over MUMF-G is just a quotient by the action of out FG. And this is not actually injective. So this is what is in the last section of our paper, to show that this is surjective but not injective. And so it's kind of related to some work of Martin on his paper Non-Archimedean Schottky space and its tropicalization, because he basically builds a Schottky space that resembles more this kind of object on the right. So it was kind of nice to see that there is a relation, but they're not quite the same space here. Okay, so that was my last slide, more or less. I mean, there's a lot of other projects that we have in mind with Jérôme to extend this construction, but maybe I should just end this here.